In one of the deepest images ever taken of the night sky, there's a tiny red smudge no wider than a strand of hair held at arm's length. You would not notice it if no one pointed at it. You could stare at the picture for an hour, and your eyes would skim past it, settling on the brighter, prettier galaxies, the swirls and spirals and ovals that look like proper cosmic things. The smudge would sit there, patient, the way it has been sitting in space for almost the entire age of the universe, waiting to be noticed, waiting to be understood. But that smudge is a galaxy, and that galaxy is the oldest thing humanity has ever seen. It existed when the universe was less than 2% of its current age. Less than 300 million years had passed since the Big Bang, when the light we are now looking at first left it. Stars themselves were a new invention. Heavy elements were rare. The cosmos had barely learned how to make light. And yet, somehow, an entire galaxy was already burning there, fully formed, already too bright, already too big, already breaking the rules of every theory that said this should not be possible yet. Tonight, we're going to walk to that smudge. Slowly, layer by layer, across 13.5 billion years of empty, expanding space. We will start where you are sitting right now and end at a place where the universe was still warm from its own birth. We will look at how the light got here. We will look at what it tells us. We will look at why the people who found it could not stop checking their numbers again and again, hoping they had made a mistake. And we will look at what it means that they had not. There is no rush. Settle in. Let your shoulders drop. The journey is long, the universe is patient, and the smudge has waited this long. It can wait a little more. We begin. When you step outside on a clear night and look up, the sky feels finished. The stars are arranged in patterns. The moon is in its place. A few planets, if you know where to look, hold their slow paths along the same band the sun follows during the day. Everything seems to be where it has always been, and where it always will be. The whole picture has the quiet authority of something completed. This is not how the universe works. Every point of light reaching your eye is old. Some of it has traveled for years, some for centuries. The starlight you see from the brightest stars in your local sky has typically been moving for decades or even thousands of years before arriving at your retina. By the time it gets to you, the star itself may have changed or moved, or in rare cases even died. You are not looking at the night sky. You are looking at a record of the night sky, a delayed photograph, where every pixel was developed at a different moment in cosmic history. The light from our nearest galaxy, Andromeda, took about 2.5 million years to reach us. When that light left, our ancestors were not yet using stone tools. The light from the most distant objects you can see with the naked eye is about 3 million years old. The light from the most distant objects amateur telescopes can detect is older still. And the light from the most distant objects ever observed by humanity is so old that it predates the formation of the Earth, the Sun, and almost every star you have ever known. This is the first thing you have to feel in your body before we can travel further. The night sky is not a place. It is a stack of times. Each layer of it carries a different age, a different version of the universe, written in light that has been moving across expanding space for as long as that distance demanded. Now imagine peeling those layers back. Imagine asking what is underneath the most distant thing you can see. Imagine going further, past the visible galaxies, past the local cluster, past the great filaments of the cosmic web, past the quasars, past the early structures, until you reach a place where the universe itself was still being assembled. There's a moment, deep in that direction, where the light becomes so old, so stretched, that ordinary telescopes cannot see it at all. The wavelengths have been pulled into the infrared, beyond what human eyes evolved to detect. To see those layers, you need a different kind of instrument. You need a telescope that hunts for warmth, not color. A machine that listens to whispers no living creature was ever built to hear. We built one. It cost us about $10 billion, took 3 decades to plan, and was launched into space on the last day of 2021. And the first time it pointed at the deepest darkness we knew, it found something that should not have been there yet. That is where we are going tonight, toward the thing it found. But first, we have to understand the instrument that found it, because the journey is impossible without knowing what kind of eye is doing the looking. The James Webb Space Telescope is the largest, most expensive, most sensitive observatory humanity has ever placed in space. It launched on December 25, 2021, on a French Ariane rocket from the coast of South America. Inside its protective fairing, folded like a piece of cosmic origami, was a mirror nearly 21 feet across, made of 18 hexagonal segments coated in a microscopic layer of pure gold. The gold is not for show. Gold reflects infrared light better than almost any other material on Earth, and infrared light is what this telescope was built to drink. After launch, the telescope had to unfold itself in a sequence so delicate that hundreds of single points of failure had to all go right, in the cold of space, with no chance of repair. The sun shield, the size of a tennis court, deployed in 5 thin layers, each one designed to drop the temperature of the telescope by a precise number of degrees, until the cold side was hovering near minus 400 degrees Fahrenheit. The mirror segments aligned themselves, tilting in nanometers, until they functioned as a single, perfect surface. And then, 6 months after launch, the telescope began to look. The reason it looks in infrared is not arbitrary. The reason is the universe. Imagine an ambulance siren passing you on a quiet street. As the ambulance approaches, the sound is high. As it leaves, the sound is low. The waves are stretched by the motion of the source. Light works the same way. When the source of the light is moving away from you, the wavelength stretches, and the color shifts toward the red end of the spectrum. Astronomers call this redshift. And the universe, as we have known for almost a century, is expanding. Every distant galaxy is moving away from every other distant galaxy. The further the galaxy, the faster the recession. The faster the recession, the more its light is stretched. At extreme distances, the visible light a galaxy emitted has been pulled all the way out of the visible spectrum entirely, into the infrared, and then deeper still. Hubble, the great telescope of the previous generation, could see invisible and a small slice of near-infrared. It found galaxies billions of light-years away. It pushed the edge of the observable universe further than any instrument before it. But there is a horizon Hubble could not cross, a horizon beyond which the light has been stretched so thoroughly that it no longer falls in any wavelength Hubble was designed to detect. Past that horizon, Hubble was blind. The James Webb Space Telescope was built to see past that horizon. Its instruments are tuned for infrared. Its mirror is huge to gather as much faint light as possible. Its location, almost 1,000,000 miles from Earth at a gravitational balance point called L2, places it in permanent cold, permanent darkness, permanent peace. It is the cleanest, deepest, hungriest eye humanity has ever built. And in its first year of operation, it began the work of looking back further than anyone had ever managed before. One of the largest projects it accepted was a survey called JADES, the JWST Advanced Deep Extragalactic Survey. The name is technical. The intent was simple. Stare at one small patch of sky, longer than any patch of sky had ever been stared at before. Use the deepest exposures the instrument could manage. Photograph everything in that patch, no matter how faint. Then, with spectroscopy, measure the redshift of every interesting object, and use those numbers to figure out how far away each object actually was, and how far back in time we were seeing it. The first set of JADES images was released in late 2023. Astronomers across the world began combing through them. Most of the galaxies in the field were already known, or were the kind of distant objects everyone expected. But buried in the data was a tiny red smudge that looked, at first, like an artifact, or a fluke, or a foreground object playing tricks. The team marked it for a closer look. They could not have known yet that this faint red was about to become the most distant confirmed object in the history of human observation. To understand what an image like this is, you have to understand how astronomers stare. They do not glance. They do not photograph. They expose. The shutter on a deep-field image is held open for hour after hour, sometimes spread across many days, sometimes spread across an entire year of observations, layered together to drag the faintest possible signals out of the noise. The patch of sky JADES targeted is a region called Good South in the constellation Fornax. Fornax is a small southern constellation, not flashy, not famous, just a quiet, faint set of stars. The patch itself is so small that if you held a grain of sand at arm's length, the grain would cover more sky than the deepest part of the JADES field. And yet, in that grain of sand of sky. The telescope eventually counted thousands upon thousands of distinct galaxies, scattered across nearly the entire age of the visible cosmos. When you look at the final image, the closest galaxies are large and detailed. Spiral arms, bright nuclei, the familiar shapes you recognize from textbooks. Behind them sit smaller galaxies, more compact, often more distorted, their forms shaped by the violent collisions and mergers of an earlier era. Behind those, still smaller, are the very early galaxies, mostly red, mostly faint, mostly compact little blobs that astronomers call dropouts because they appear in the long wavelengths and disappear in the short ones, exactly as predicted for objects whose light has been stretched by enormous redshift. Every dropout is a candidate. Every candidate has to be confirmed. Photometry, the measurement of brightness across different wavelength filters, can give you a guess at how far away a galaxy is. Spectroscopy, the careful breakdown of the light into its component colors, gives you the actual answer. Each candidate galaxy in the JADES field had to be observed not just once, but many times, with a spectrograph instrument called NIR-SPEC, which could split the light into a fine ladder of wavelengths and pin down the redshift to a precise value. Among the candidates, one stood out. It was redder than expected. It was brighter than it had any right to be. It sat near the edge of what the photometry could even classify. The team gave it a workmanlike name, the kind of label that makes scientific papers feel less personal than they actually are. They called it JADES GS, Z14-0. The GS stood for the Good South field. The Z14 stood for the predicted redshift, around 14. The 0 stood for the most extreme candidate at that redshift in the field. Just a string of letters and numbers. Nothing in the name hinted at what was about to happen. The team scheduled a deep spectroscopic observation. They booked time on the telescope. They wrote the observation plan. They waited. And then the data came down. The first thing the spectrum showed was a feature called the Lyman break. The Lyman break is one of the most useful tools in the early universe astronomer's toolkit. It is a sharp drop in the spectrum at a specific wavelength, caused by the way neutral hydrogen in space absorbs light below a certain energy. The wavelength at which this drop appears tells you how much the light has been stretched on its way to you. From the position of the break, you can read the redshift like the date on a postcard. The break in the spectrum of JADES GS, Z14-0 sat where redshift 14.32 would put it. 14.32. That number on its own looks small. It is only a number. But when you translate it back into time, into distance, into the age of the universe at which this light was emitted, the number becomes something else entirely. 14.32 means the universe had to expand by a factor of more than 15 since the light left the galaxy. 14.32 means we're looking at the galaxy as it existed when the universe was less than 300 million years old. 14.32 means we are looking at light that has been moving toward us for about 13.5 billion years. Hold that for a moment. 13.5 billion years. If you were to spend 1 second of your life for every year the light has been traveling, you would have to live more than 425 times the entire current age of the universe just to count out the journey. The light is older than the sun by about 9 billion years. It is older than the Earth by about 9 billion years. It is older than every fossil ever discovered, every continent ever named, every ocean ever filled, every mountain ever raised. It started its journey in a universe that was just under 300 million years past the Big Bang, when every cosmic clock was reading early, and it has been moving ever since, across an expanding space that has stretched it from ultraviolet into deep infrared, until it finally arrived at a gold-coated hexagonal mirror parked at L2, late in the year 2023. And the galaxy that emitted that light was not what anyone expected to find. It was 1,600 light-years across. That sounds small for a galaxy. The Milky Way is about 100,000 light-years across. JADES GS, Z14-0 is roughly 1/60th of that diameter. Compact. Tiny by Milky Way standards. A baby galaxy. But here is the problem. Inside that 1,600 light-year span, there were enough stars to make the galaxy visible across 13.5 billion years of expanding space. The team estimated its mass at hundreds of millions of times the mass of our Sun, possibly approaching 500 million solar masses, by some analyses. That is a staggering amount of starlight to gather inside such a small volume, in such a young universe, in so little time. The light reaching us was not coming from a growing supermassive black hole, the way it does in some early bright objects. It was coming from stars. Real, ordinary, fusion-powered stars. A lot of them. Burning fast. Burning bright. Already there. The team checked their numbers. They found nothing wrong. They looked again. Still nothing wrong. The galaxy was real. The redshift was confirmed. The brightness was honest. JHGS Z14-0 had existed, fully formed, less than 300 million years after the Big Bang, and it had no business existing at all. Let us pause here, because the next steps will only land if you feel, in your body, what is meant by a redshift of 14. Numbers can be slippery. They are easy to read and hard to feel. But this number in particular is the engine of everything we are about to discuss, and it deserves a moment of careful attention. Imagine you are sitting in an empty field, and someone is walking away from you slowly. As they walk, they start to sing a single steady note. The note is high. As they recede, you would still hear the note as high, because their walking speed is small compared to the speed of sound. But now imagine they begin to run. The faster they go, the lower the note sounds to your ear. If they could somehow run away faster than sound itself, the note would never reach you at all. If they could run away at almost the speed of sound, but not quite, the note would still reach you, but stretched into something deep and slow, a long-held tone, almost no longer recognizable as music. Light works in a similar way, but with a twist. Light has a finite speed, and light always travels at that speed in a vacuum no matter what. So when a galaxy is moving away from you because the space between you is stretching, the light it sends does not slow down. The light keeps moving at the same speed, but the wavelength stretches, in step with the expanding space the light is traveling through. By the time the light arrives at your telescope, every peak and trough of a wave has been pulled apart, the same way a long rubber band gets pulled longer the further you stretch it. Redshift 14 means the light has been stretched by a factor of about 15. Visible light, when it left, has arrived as deep infrared. Ultraviolet light, when it left, has arrived as the wavelengths the James Webb Space Telescope was specifically designed to detect. The factor of 15 is not just a number on the spectrum. It is the factor by which the entire universe has expanded since the light left. The space between us and the galaxy has grown to 15 times what it was when the photons began their trip. There's one more piece of this picture that quietly bends the brain. The galaxy was not 13.5 billion light-years away when it sent the light. It was much, much closer, possibly only a couple of billion light-years away, by the kind of distances physicists call comoving. The light only had to travel through a relatively young, smaller universe at first, but as the universe expanded, the road the light was on kept stretching, faster than the light was traveling. By the time the photons reached us, they had been moving for 13.5 billion years, and the galaxy that sent them was now, by that comoving measure, more than 30 billion light-years away. Read that again. The galaxy that sent the light is now more than 30 billion light-years away from us, and the universe is only 13.8 billion years old. The galaxy is further away in space than the age of the universe in time, because space itself has been expanding faster than light could cross it. None of this violates physics. It only violates intuition. Space can stretch as much as it wants. The speed limit applies to objects moving through space, not to space stretching itself. Hold all of this together for a moment. The smudge was once close. Then space grew. The light kept coming. And now the light is here. The galaxy is far, and the cosmos between us, and it is 15 times the size it used to be. A galaxy living in a younger, smaller universe sent us a postcard, and the road it took has been stretching the whole way. This is the geometry of seeing back in time. Every old photon you collect comes from a place that no longer looks the way the photon shows it. The image is real. The galaxy still exists, somewhere out there, almost certainly utterly transformed by now, perhaps long since merged with other galaxies, perhaps the seed of something much larger. But we will never see it any way other than the way it was when this light departed, because by the time any signal of its later years could reach us, The universe might no longer be a place that allows the signal to travel here at all. The smudge is a fossil, not a metaphor, a real, optical, ancient fossil, as old as the universe permits us to see, recorded in a single faint speck on a single deep image, captured by an instrument hovering 1,000,000 miles above your head while you sit somewhere quiet and listen to this. A galaxy is supposed to take time to build. The standard story of how galaxies form, the story most working astronomers learned in graduate school, the story that fits most of the data we had before JWST, goes something like this. After the Big Bang, the universe was a hot soup of charged particles, mostly hydrogen and helium, with no real structure at all. As the universe expanded and cooled, those particles eventually combined into neutral hydrogen atoms, an event called recombination, which happened around 370,000 years after the Big Bang. Recombination released the famous cosmic microwave background, the oldest light we can see, the static glow that fills every direction we point a sufficiently sensitive radio telescope. After recombination came the cosmic dark ages. No stars yet, no galaxies, just slowly cooling clouds of neutral hydrogen, sitting in the gravitational wells of dark matter, drifting toward concentrations dense enough to begin collapsing. The first stars are believed to have formed somewhere between 100 and 200 million years after the Big Bang, give or take, depending on which simulation you trust. Those first stars were enormous, short-lived, and made entirely of hydrogen and helium. When they exhausted their fuel, they exploded as supernovae and seeded the surrounding gas with the first heavier elements, the carbon, nitrogen, oxygen, and so on, that would later become the raw material of every later star and planet. The first galaxies, in this picture, were small, faint, and slow. They began as little clumps of stars in growing dark matter halos. They merged. They grew. They formed disks. They grew bigger. And only after several 100 million years of patient assembly did they become bright enough, massive enough, and chemically rich enough to look like the things we recognize as proper galaxies. Jade's GS Z14-0 does not fit that picture. It is too bright. It is too massive. It is too compact. It is too soon. It contains hundreds of millions of solar masses worth of stars, packed into a volume only a few thousand light years across, less than 300 million years after the Big Bang. By the rules of the slow build-up model, the universe should not have had time to assemble this much organized starlight by this point in its life. The galaxies of this era were supposed to be tiny, dim, and growing. Instead, here is one already shining, already structured, already heavy. The lead astronomer on the spectroscopic confirmation, Stefano Carniani of the Scuola Normale Superiore in Italy, said something quite revealing when the result was announced. He said it was stunning that the universe could make such a galaxy in only 300 million years. Stunning is not a word astronomers use casually. Stunning is the word a careful scientist uses when the data is correct, the analysis is correct, and the implications are correct, and the implications are still difficult to accept. The galaxy is real. The numbers are real. And the universe, evidently, can do something we did not believe it could do. Some of the team's first reaction was the standard scientific suspicion. Maybe the brightness is not coming from stars. Maybe there is a growing supermassive black hole in the center, an active galactic nucleus, that is the actual source of all that light. Active galactic nuclei can outshine entire galaxies, and they can fool you into thinking a galaxy is much more massive than it is. So the team checked. They looked at the size of the bright region. An active galactic nucleus would be a point source, basically zero size at this distance. The bright region in Jade's GS Z14-0 is a full 1,600 light-years across. That is far too large to be a single black hole. The light is coming from stars, a great many stars, distributed over a real volume, burning real fusion. The galaxy is made of stars, and the stars are already there. And then, the universe twisted the knife. Before any astronomer is allowed to claim that a discovery breaks a model, the rest of the field gets to try, very systematically, to break the discovery. This is one of the quiet rituals of science. You do not get to call something impossible until every possible mundane explanation has been walked through, tested, and either confirmed or ruled out. The team behind Jade's GS Z14-0 knew this perfectly well. So did everyone else looking at the data after them. The community went through the standard list of escape routes, one by one, and watched each one close. The first escape route was simple. Maybe the redshift was wrong. Maybe the spectroscopic line that looked like a Lyman break at redshift 14 was actually a different feature at a much smaller redshift, and the galaxy was nearby and ordinary, only pretending to be ancient. This kind of mistake has happened before in deep field work. A foreground galaxy, with the right kind of dust, can mimic the colors of a high redshift object. The team checked. They obtained more spectra. They got a confirmation from a second instrument. The redshift held. The wavelength of the break was real. The galaxy was where the number said it was. The second escape route was that the galaxy might be a fluke. Maybe one strange object had wandered into the deep field by accident, and the rest of the early universe was perfectly well behaved. The team checked. They looked at the broader catalog of high redshift candidates from JADES and from other JWST surveys. They found that JADES GS Z14-0 was not isolated. There were many bright early galaxies, more than any model had predicted. One smudge could have been an accident. A whole population could not. The flagship was just the most extreme example of a much wider pattern. The third escape route was the active galactic nucleus, the one we already mentioned briefly. The size of the bright region ruled it out. A point source would not be 1,600 light-years across. The fourth escape route was gravitational lensing. Maybe a foreground galaxy or cluster had bent the light of a more ordinary background galaxy and made it look brighter than it really was. This happens routinely in deep field surveys, and is often how some of the most distant objects in the universe become visible at all. The team looked for the foreground lens. They found nothing strong enough to explain the brightness. The galaxy was bright on its own, by its own power, with no help from a cosmic magnifier. The fifth escape route was instrument error. Maybe some quirk of the detector, some calibration issue, some flat field problem was producing a phantom galaxy where none existed. The team rechecked the calibration. The galaxy showed up in independent observations, with independent reductions, by independent groups. It survived every test. It was real. Each escape closed in turn. The team had to accept what the data said. The galaxy was bright. The galaxy was massive. The galaxy was old. The galaxy was real. The model that said this should not be possible yet had a problem, and the problem was not going to go away by itself. Real science feels like this most of the time. It is not a triumphant march from confusion to enlightenment. It is a long, careful walk, room by room, closing every door behind you, until the only room left is the one you had hoped you would not have to enter. The room marked, our model is incomplete. The room marked, the universe knows something we do not. The team entered that room with the first JADES results, and they have been sitting in it, taking notes, ever since. In early 2025, a separate result came in, not from the James Webb Space Telescope this time, from a different instrument entirely. The Atacama Large Millimeter Array, known as ALMA, is a giant collection of radio dishes high in the Chilean desert, designed to listen to the cold, faint, longest wavelengths of radiation a galaxy can emit. Two independent teams pointed ALMA at JADES GS Z14-0, and they were both looking for the same fingerprint, a specific spectral line, at a specific submillimeter wavelength that is emitted only by ionized oxygen. Oxygen is the third most abundant element in the modern universe, but it was not present at the Big Bang. Only hydrogen, helium, and a tiny pinch of lithium emerged from the initial cosmic furnace. Every oxygen atom in your body, in your lungs, in the water you drink, in the rocks under your feet, in the atmosphere that supports the trees outside your window, was made inside a star. To get oxygen into a galaxy, you have to first build a generation of stars, wait for them to live their lives, watch them die in supernova explosions, and then collect the oxygen they spit out into the surrounding gas. The gas, enriched with oxygen, can then form a second generation of stars and planets. This is the mechanism by which the universe slowly accumulates heavy elements over cosmic time. Both the LMA teams found oxygen in JADES GS Z14-0. Not a trace, not an upper limit, A clear, confident detection of ionized oxygen in a galaxy whose light left it less than 300 million years after the Big Bang. The amount of oxygen, when carefully analyzed, was about 10 times higher than the simplest theoretical models had predicted for a galaxy of this age. The implication was unmistakable. By the time we see this galaxy, it has already hosted at least 2 generations of stars. The first generation was born, lived, exploded, and seeded the gas with oxygen. The second generation then formed from that enriched gas, and is what we are looking at now. 2 stellar generations, complete with the deaths of the first, all packed into the very early universe, in a galaxy that itself looks like it should still be a baby. Sander Schouws, a doctoral candidate at Leiden Observatory in the Netherlands, who led one of the 2 ALMA studies, described the find with a phrase that has been repeated by every astronomer who has tried to summarize the result. He said it was like finding an adolescent where you would only expect babies. Sit with that image for a moment. The early universe was supposed to be a nursery. It was supposed to be the place where the first stars were just starting to clear the dark ages, where the first faint galaxies were just beginning to form, where everything was small, dim, slow, and mostly made of the simplest possible matter. And instead, deep in that nursery, the JWST and ALMA together had found a galaxy that was already chemically mature, already bursting with the products of stellar death, already running its furnace at a rate fast enough to forge the third most abundant element in the cosmos and store it in detectable quantities, less than 300 million years after time itself, in any meaningful cosmic sense, had begun. The discovery did not just push the record back. It changed the kind of question astronomers were allowed to ask. The new question was no longer how early can we find galaxies. The new question was how early can the universe make a mature galaxy? And nobody had a confident answer. Every model is a story. Cosmologists tell themselves stories about how the universe assembles itself, and then they test those stories against the data. When the data agrees, the story stays. When the data disagrees, the story has to change. Science is the slow, careful, often reluctant process of letting go of stories that no longer fit. The story of slow galaxy buildup had stood for a long time. It was a good story. It explained the great variety of galaxies in the local universe. It explained the merger trees that astronomers traced through generations of simulations. It explained the subtle properties of nearby spirals and ellipticals, the chemistry of their stars, the distribution of their masses. The story did not need rewriting often. It was settled physics, more or less, with rough edges that everyone agreed would be tightened up over the next few decades of careful observation. Then JWST started reporting results, and the rough edges turned out to be load-bearing. The slow build-up story predicted a smooth decline in the number of galaxies as you looked further back in time. Each step further back should have given fewer galaxies, smaller galaxies, dimmer galaxies, until you reached an era so early that there were essentially no galaxies at all. JWST has, instead, found a population of bright galaxies at very high redshifts that is roughly 10 times larger than the pre-JWST extrapolations had predicted. Galaxies that should have been rare and faint at this era of the universe are showing up instead as common and bright, as if the universe figured out how to make stars much faster than the standard simulations allowed. JADE's GS Z14-0 is not an outlier. It is a flagship example of a much broader anomaly. The early universe, as JWST is mapping it, is more vigorous, more crowded, and more chemically advanced than the previous generation of theory expected. Across the whole high redshift frontier, astronomers are seeing galaxies that look too organized, too bright, too heavy, too soon. The smudge is just the most extreme case. The pattern goes well beyond it. Several explanations are on the table. Maybe early stars were unusually massive and burned brighter for their mass than later stars. Maybe early galaxies were unusually efficient at converting their gas into stars, faster than any later epoch could match. Maybe the dark matter halos that hosted these early galaxies were unusually dense, allowing more rapid collapse and ignition than later, more diffuse halos. Maybe the dust in early galaxies was unusually low, letting more of their light escape outward, making them look brighter than they really should. Maybe several of these things are true at once, and the slow build-up model needs not just adjustment, but rebuilding from the foundation up. Nobody is panicking. This is not a crisis in the sense of a paradigm collapsing. The Big Bang model itself is fine. The general expansion is fine. Dark matter and dark energy are fine. The cosmic microwave background still says what it has always said. What has changed is the local detail of one chapter, the chapter on early galaxy formation, which had been treated as broadly settled and is now revealed to be only roughly understood. The textbook needs revision. The simulations need new physics. The story has to change. And the smudge is the page where the change is being written. 18 months after Jade's GS, Z14-0 took the title of most distant known galaxy. The title was taken from it again. On the 16th of May, 2025, a different team, led by Rohan Naidu, working from the Cosmos Legacy field instead of Good South, used JWST to confirm a galaxy at a redshift even higher than Jade's GS, Z14-0. The new galaxy was given the name MOM, Z14. Its redshift was measured at 14.44. That is only a small numerical step beyond 14.32. But in the geometry of the early universe, even small steps count for a lot. MOM, Z14 existed when the universe was about 280 million years old, 20 million years earlier than Jade's GS, Z14-0, earlier than the previous record holder, by enough cosmic time to let astronomers see one more layer further back into the dark, into the very first chapters after the cosmic dawn. The light had been traveling for about 13.53 billion years before it arrived at the JWST detectors. The fraction of the universe's age at the moment we are now seeing MOM, Z14, is about 2%. MOM Z14 is small. Its effective radius is only about 240 light-years, roughly 1% the size of the Milky Way, far smaller even than Jade's GS, Z14-0. Compact, tight, almost a point of light. But again, the brightness is wrong. It is far brighter than a galaxy that small at that age should be allowed to be. And the spectrum carries something even stranger than oxygen. It carries nitrogen. It carries carbon. It carries helium. Different ionization states of all of them. Glowing and clean emission lines that the team could measure precisely. Nitrogen is rarer in the early universe than oxygen. To make nitrogen at all, you need a particular kind of stellar nucleosynthesis, usually associated with stars that have already gone through advanced burning stages. To find nitrogen this strong, this early, suggests a stellar population that is very young in calendar time, but already chemically rich beyond what should be possible. The team noted that the abundance pattern resembles what is sometimes seen in modern globular star clusters, those tightly bound ancient swarms of stars that orbit galaxies like ours. Some theories suggest those clusters might once have hosted enormous, short-lived, supermassive stars, capable of producing exactly this kind of unusual element ratio. MOM Z14 might be giving us a real-time look at a process that, by the time we observe its descendants in the local universe, is already over and gone. And then there is the most disquieting detail of all. The light from MOM Z14 shows little sign of being absorbed by surrounding neutral hydrogen on its way out of the galaxy. Every model of cosmic reionization predicts that, at this redshift, almost the entire universe outside the galaxy should still be filled with neutral hydrogen, the atomic gas left over from recombination, not yet ionized by enough early starlight or quasar light to become transparent. Galaxies in this era should be embedded in fog. Their light should be partially eaten on the way out. The fact that MOM Z14 spectrum does not show the strong damping wing expected from this fog is a quiet little statistical signal that says something around this galaxy is already partially ionized. A bubble of clarity, a pocket of cleared gas, in a universe that should still be opaque. We do not know how big the bubble is. We do not know how the bubble formed. We do not know whether it is the work of MOM Z14 itself, or of nearby unseen sources, or of some combination of structures that we have not yet imaged. What we know is that the galaxy is sitting in a region of the early universe where the cosmic fog is thinner than the textbooks said it would be. That on its own is a hint, a small one, a faint one, but a hint that the early universe was not quite as uniform Not quite as simple, not quite as slow as we used to assume. Peter Van Dockum, the Yale astronomer who led the team's spectroscopic confirmation of MOM Z14, said something almost meditative when the result was announced. He said, of the galaxy, that this was the most distant object known to humanity. He noted that the title would change again, eventually, the way it always does. But for now, MOM Z14 is the deepest layer of the night sky. It is the furthest back any human has ever seen anything anywhere. And it carries with it the same uncomfortable message JHGS Z14-0 already delivered, only sharper. The universe assembles itself faster than we thought. The first galaxies were busier than we thought. The dark ages were not as dark, or as patient, as we used to teach. When one anomaly appears in a settled field, scientists usually assume the anomaly will turn out to have a quiet explanation that does not require rewriting the larger story. When two anomalies appear, with similar shape, in the same era, in the same kind of object, the assumption begins to weaken. When a whole population of anomalies appears, all pointing the same direction, the larger story has to be examined seriously. JHGS Z14-0 was one anomaly. MOM Z14 made it too. The wider population of bright early galaxies that JWST has been finding makes it many, and the questions that flow from that are now much bigger than any single galaxy. The first question is about reionization. Reionization is the chapter of cosmic history when the neutral hydrogen left over from recombination got broken apart again by ultraviolet light into ionized hydrogen and free electrons. This is what made the universe transparent in the first place. Without reionization, the cosmos would still be a fog. Astronomers had assumed reionization was driven mostly by light from a slowly growing population of early galaxies, building up over hundreds of millions of years, finishing the job sometime around 1 billion years after the Big Bang. But if early galaxies were already bigger, brighter, and more chemically advanced than the slow build-up story allowed, then they were also producing far more ultraviolet photons than the textbook predicted, far earlier. Reionization may have started earlier. It may have proceeded faster. The bubble of clear gas around MOM Z14 hints at this. Future surveys will test the hint. The second question is about the very first stars. The slow build-up story imagines the first stars, the so-called population 3 stars, as huge, hot, short-lived objects that lived briefly, exploded, and seeded the gas with the first heavy elements. The chemistry inside JHGS Z14-0 and MOM Z14 says those first stars finished their work earlier than expected. Either there were more of them than the simulations allow, or they made heavy elements more efficiently than the simulations allow, or they finished sooner than the simulations allow. Maybe all three. The first stars are still beyond direct observation, hidden in eras even older than the smudges, but the chemistry of the smudges is one of the only ways we have to study them at all. And the chemistry says, build new simulations. The third question is about dark matter. The way dark matter halos collapse and grow is one of the foundations of every galaxy formation model. If early galaxies are heavier and more developed than the standard model expects, one possible response is that the dark matter halos hosting them must also be denser or more efficient, or that some additional physics is letting gas collapse into stars faster inside them. Some theorists have started exploring whether properties of dark matter itself, things like its self-interaction, or its initial fluctuation spectrum, might need adjustment. Most of the field is still cautious. None of these adjustments are required yet, but they are now on the table, in serious conversation, in a way they were not 5 years ago. None of this is collapse. The Big Bang is not in trouble. The expansion of the universe is not in trouble. The basic shape of cosmic history is not in trouble. What is in trouble is the detailed story of one chapter, the chapter on early galaxy formation, which was treated as broadly settled and is now revealed to be a working draft. Working drafts get revised. The revision is happening in real time, in seminars, in arcs of preprints, in graduate student offices, in coffee conversations between collaborators, while the rest of us go about our days largely unaware. The textbook of the next decade will not look like the textbook of the last decade. Quietly, slowly, the smudges are doing the work of changing it. And there is something almost beautiful about that. The cosmos does not need to scream to make you rewrite your theory of it. It only needs to whisper, in the form of a single faint of red light, in a small corner of the sky, that the schedule was not what you assumed. The universe was always quicker than the simulations. We are only now learning how to listen carefully enough to hear it. Every record holder is temporary. That is a small, important truth about deep cosmology. Whatever the most distant known galaxy is at any given moment, there is, almost certainly, a more distant one, somewhere in the sky, whose light is still arriving but has not yet been resolved. The James Webb Space Telescope is still in its early years. The instrument can run for at least another decade, possibly longer. New surveys are being planned. New patches of sky are being targeted. Every fresh deep field has the chance of carrying inside it a still older, still smaller, still redder smudge. There is an upper limit to how far back any telescope, in principle, can see. Past a certain point, the universe is opaque. Before the cosmic microwave background was released, the universe was a hot plasma in which light could not travel freely. That is a hard wall. No optical or infrared telescope, no matter how powerful, can see past the cosmic microwave background using ordinary light. If you want to see further back than that, you need different physics. You need to look for relic signals from gravity, or from neutrinos, or from other faint messengers that could survive an opaque universe. Those instruments do not yet exist at the precision required, but they are being designed, slowly, carefully, by people who know that the deepest layers of the night sky are not yet finished revealing themselves. Between MOM Z14 and the cosmic microwave background, there's a window of about 250 million years that is currently mostly dark. Most of those galaxies are too dim, too small, too rare to find with any current survey. But they are out there. Their light is in motion. Some of it is already entering the upper atmosphere of Earth right now. Some of it has been absorbed by the gold mirror of JWST and recorded, but not yet picked out from the noise. Somewhere in the next round of analysis, in the next data release, in the next paper, the smudge that takes the title from MOM Z14 will appear. It will be smaller. It will be older. It will look like nothing at first. A computer will flag it. A team will check it. And the layer beneath the most distant known galaxy will become the new most distant known galaxy. The light of every future record holder is already on its way. It has been on its way for billions of years. It will arrive without ceremony. It will become a measurement, then a paper, then a press release, then a news story for a few days, then a new line in a textbook. And the cosmic story will quietly, slowly, get rewritten one more time. The smudges keep coming. The night sky keeps unfolding. The universe is patient. It will keep handing us its earliest fossils, one at a time, for as long as we keep building the eyes to receive them. It is hard to feel, fully, what it means to be alive in a moment when the deepest layers of the night sky are being peeled back for the first time. People have looked at the stars for as long as there have been people. Almost every culture, in almost every era, has decided that the sky was important, that the sky carried meaning, that the sky was somehow connected to the question of where everything came from. They told stories. They drew maps. They named the brightest points. And mostly, they had no real idea what they were looking at. The sky kept its secrets, partly because the secrets were too far away to read, and partly because the right instruments simply did not exist yet. We are the first generation that can actually see the early universe, not as theory, not as speculation, as an image, a real, faint, deeply red image, taken by a telescope behind the cold side of a sun shield 1,000,000 miles from Earth, of a galaxy that lived when the universe itself was a toddler. The smudge is not a metaphor. It is a photograph of the past. The light is real. The galaxy is real. The shock the astronomers felt was real. And the new humility about how the cosmos works is also real. There is something quiet and strange about all of this. A galaxy 13.5 billion light years away does not change anything in your daily life. Whether the early universe assembled itself slowly or quickly, the morning will still arrive at its usual time. The bills will still need paying. The people you love will still need their share of attention. None of this private, planetary, Human living is touched by the news that a galaxy nobody has ever heard of is too bright for its age. And yet, somehow, the smudge does change something. The fact that we know it exists, the fact that we can name it, the fact that humans built a machine and pointed it at one small patch of sky and pulled out of the noise a single feint of light older than the sun, the earth, and almost everything you have ever cared about, has a way of quietly readjusting your sense of what is going on. We are sharing a universe with this thing. Our atoms came from stars that were the cousins of the stars that lived in Jades, GS, Z14-0. The cosmic chemistry that gave you oxygen to breathe is a continuation of the chemistry that surprised the astronomers when they detected it in a galaxy nearly 14 billion years ago. The story of you is not separate from the story of the smudge. The story of you is downstream of it. And there's one more thing. The astronomers who confirmed Jades, GS, Z14-0 used a phrase that hangs around in your head if you let it. They said the galaxy is more mature than expected. The first generation of galaxies, they wrote, assembled their mass very quickly. The universe, evidently, was already in a hurry. From the very beginning, the Dark Ages were not a long, quiet pause before the show started. The show was already starting before anyone thought it could, and the show has never stopped. You are sitting at the latest moment of it. The cosmic story that began in one hot, dense, tiny moment 14 billion years ago, and that produced a too-bright galaxy in less than 300 million years, has continued without pause. It has built every star you have ever seen, every galaxy, every supernova remnant, every black hole, every world, and almost incidentally, in one corner of one ordinary spiral, on a small rocky planet, a species of curious primates eventually figured out how to take pictures of the very beginning of all of it, and is now slowly, patiently, gently learning what those pictures actually mean. The smudge sits there on the JWST image, unchanged, still red, still faint, still impossible by the old rules. The universe has not finished surprising the people who study it. It has not finished surprising you either. It made it. You are here for its arrival. The journey ends, for now. Sleep softly. The universe is in no hurry. Before we close, two small things. If something in this journey moved you, even a little, leaving a comment with the word smudge would help others find this place, and would let me know you walked the whole way. If you found the calm in this useful, subscribing and letting the notifications stay quiet means the next deep field, the next record holder, the next strange chapter of the early universe will arrive at your door without you needing to remember to look for it. There are more layers underneath this one. We will visit them together, slowly, when the time is right. Until then, may your sleep be deep, may your breath stay slow, and may the night sky overhead keep you company until morning. Good night.